Got it. Open system.
Okay, so welcome everyone.
Plus.
Welcome everyone. We're very happy to have Ilan Newman with us from the University of Haifa. Ilan, as you know, has been with this seminar even before it went on Zoom. In the years when we ran it in person, when Jasin and Rogers and Deepak were in Haifa, we had a really nice weekly seminar. And then once we weren't able to meet in person, we started the Zoom version of it for the last 2.5 years. But Ilan is a longtime member and even leader of the seminar. So I'm very happy that you're giving a talk today, along with several other work with several other visitors to Haifa, like Nithin. And so take it away, Ilan.
Okay, so tell me if you can hear me first, because I'm. It seems that I'm having some problem.
Yes.
Okay,
Oh,
that's good. And you can also see the presentation, right?
Yes, but we don't understand the proof yet.
Okay. Okay, so maybe, yeah. So it's a good time for a disclaimer, right? Okay, so thank you very much for inviting me. And it's a good time for a disclaimer. It seems that not everything is working perfectly here, especially the internet is not working perfectly, but hopefully it will go through. It will go through. Okay, so let's start then. And another thing, I welcome everybody to interfere in every possible moment. So if you have questions, just pop in and ask. Okay, good. So the title is Testing Forbidden Order Patterns in a Function. And I will need to explain what testing is and what is order pattern, and forbidden is kind of obvious. So I will start with, and that's a joint work, with Nitin Varma. Nitin was here in Israel. He was a postdoc here in Israel. Now he's in Chennai. So let me start. So how do I see the talk instead of seeing the Zoom thing? Wait, maybe this play. Well, I still see the Zoom, but okay, maybe it's not a big deal. Okay, so, it takes part of my, just a moment, I'm sorry. That's part of the technical thing. I need to get rid of all sorts of Can't I get rid of this? Okay, so I should explain you first what is property testing, and that's an area in computer science in the field that I'm working here in. So property testing is where you need to relax, or you want to relax a decision problem and kind of approximate it. So instead of just defining it proper or rigorously, in general, I will define it for the setting here. So here is the object that we are going to discuss. And you should think about them also as inputs to the algorithm. So the object is a function. So the objects are the set of functions. So an input is just a function from the discrete line of n points. So from the points 1 to n, think of them as ordered points, to the reals. So it's really a sequence. So you should think about it as a sequence of reals. And we are going to discuss decision problems of a certain type that would be this forbidden order type. But let me just, at this point, try to tell you what is property testing in general. So in general, you should think about this sequence as very, very long. So n is very, very long. I mean, approaching infinity. So you should think about it as possibly a stream, you know, of video or whatever. And you need to decide a property, and you don't even have time to read the whole stream. So you're not allowing yourself a linear time algorithm. In property testing, our goal is to have an algorithm that is much, much faster than the size of the input, which is, in this case, n. So how would we do that? Of course, for non-trivial properties, you can't expect to decide. So we need to relax something. And the relaxation is the following. We will want to decide whether our object, in this case, it's our function or our string, does it have the property? Does it have the property? Or it's far from the property, which leaves a gray area of functions that neither have the property nor that are far from the property, but that are relatively close to the property. And for this gray area, we don't mind what would the decision of the algorithm be. So if you want to kind of think about the motivation or a natural motivation for that, it's very natural in the case where you want to filter out a decision whether a system is faulty or not. Like suppose that you have this rocket, this space shuttle that you want to launch, and you want to decide that the property is the space shuttle in a perfect condition. Now, if you would want to decide it exactly, then the decision will actually be easy. You will always decide no, because a complex system like a space shuttle is never in a perfect situation. So it would be very easy to discard any input. So, but it's also not worthy at all. So what you really want to do is to accept all cases where the space shuttle is perfect or very close to perfect, and reject all cases where the space shuttle is quite far from being perfect. And in the area, this gray area in between, you don't really mind. If the algorithm would reject, saying that it found faults, then okay, it found faults, so it's okay to reject. And if the algorithm will accept, because it didn't find faults, then maybe the system is not perfect, but it's relatively close to perfect, so maybe that's okay. Okay, so in our case, of course, we are not going to talk about space shuttles. So in our case, we are going to talk about this stream. And as I told you, we are not going to read the stream. So what can you do? What is the sort of access that we have to the stream, to the function? So here is the definition of the access. You can ask for a given I, what is the value of fi? So you give a point in the range 1 to n in the domain of the function, and you ask what's the value of the function. And after a while, you need to decide whether the function has the property or it's very far from having the property. And the complexity here is a number of queries. That is the number of such access steps to the function where you define some index I and gets the value f of I. Okay, of course, not only that you need to relax, if you think about it for a moment, not only is that you had to relax the task and leave this gray area where you can do whatever you want, but it turns out that you can't expect the algorithm to be deterministic. So you really want a randomized algorithm. So we would want a randomized algorithm making quite a few queries with respect to n, to the size of the input, and that decide the right decision with very high probability. Okay, so that's property testing. Now let me move to order patterns or forbidden order patterns. So let me start what is an order pattern. So an order pattern of size k is defined by a permutation, pi in sk. You should think about k here as being constant. Like, and then through the talk, I will only consider a pattern of size 4 just for the talk. but you may think of any constant. So the result would be for any constant. And we say that the stream or the function has pi if it has a k-tuple of indices going in from left to right, such that the f order in these k indices is as in pi. Otherwise, we say that f is pi free. So note that we don't care about the values themselves. We only care about the order between the values, and we just have pi to signify for us or to signal us the relative order between values. I mean, the numerical values have no meaning at all. It's really a question about orders. Okay, here is an example. If you take pi to be the permutation 2, 1, saying that there is a high value before a low value, if f is pi free, it means that it's monotone increasing, or at least monotone non-decreasing, because we are going to talk here about strict inequalities. Okay, so being monotone is just being 2, 1 free. And here is a picture of that. So you see, here I depicted the graph of two functions. On the right, you see a function that is 2, 1 free. It's going upwards, or at least not going downwards. And on the left part, you see functions that is not 2, 1 free. It meaning that it has 2, 1 appearances. And the two red dots form 1, 2, 1 appearance. The green dots form another 2, 1 appearance. And there are another appearances as well. Okay. Here is a more complex example for a larger pattern, just for you to feel comfortable with this definition. So in this case, let me take this specific pi, 2, 4, 3, 1, 5, and the sequence is depicted below it. And you see in blue that this f has this pi appearance. And why does it have this pi appearance? Because you see it has this 90 that corresponds to a 2. Then it has 95, which is higher than 90, so it corresponds to a 4. Then it has somewhere ahead 93 that comes between 90 and 95, so that corresponds to the 3. And then the 20 and the 100 that corresponds to the 1 and the 5 for the permutation. So this f in this example is not pi free, but is it is free of the pattern 1, 2, 3, 4. Of this pattern of length 4 that is 1, 2, 3, 4, a monotone pattern, just because it doesn't have any increased sequence, any increased subsequence of length 4. Okay, so now I need to tell you, recall that our task was to distinguish between the case that has a property and it's far from the property. And our properties are going to be being pi free for a certain pi, for any constant pi. So I told you what is the property, and hopefully by now you understand well what is pi free, but what is being far from pi free? So that's the next definition. And we say that f is epsilon far from being pi free if we need to change f in at least epsilon n places so to become pi free. So here you should think about epsilon as a small constant. So for the rest of the talk, you can take it as, say, 0.01. So it's just a fixed constant, does not depend on n, could be much less than 1 over k, but it doesn't matter. Okay, so this is what is being epsilon far, and now we can go on, we are on the run. So what's an epsilon test of f, or an algorithm for this property? So as I said before, you need to distinguish between the two cases, decide whether f is pi free or it is epsilon far from pi free. And if f happens to be neither, namely it's not pi free, but it's not far, it's actually close, then you may decide whatever you want. And of course, we want to do that with high probability. Okay.
Excuse me.
So,
may I ask?
Yes, a question?
Yes. Oh, what kind of change are we allowed to do? Just replace a number for any other?
Yes, we can replace the number for any other. Yeah.
Okay.
Our functions are from F to R, and as long as we are still a function from F to R, it's okay.
Thank you.
But I will come back to this point. So in a moment. So what I've defined as distance, let me go back here. I don't know. Back too far. Why is that? I don't know, but yeah, okay. So you need so we said that it's epsilon far if you have to change at least epsilon n places, namely replace the values in epsilon n places. And it's a Hamming distance because we are measuring the number of places where you need to change the function. Note that if you have to change the function in a certain amount of places in order to make it pi-free, that certainly it is already pi-free in all places that you didn't change. Okay, so let me go on. So a brief history before going into the details into the algorithm and to this work. So monotonicity testing, as I showed you before, is just 1-2 freeness or 2-1 freeness, depending whether you want to think about monotone increasing or monotone decreasing. It's the same thing. You can always look at the sequence from backwards. So it's really two equivalent properties. And it has been studied extensively, really extensively in the last 25 years. Starting with these citations that I wrote here as EKKRV00, namely from 2000. The paper is actually from, I think, 97. It took a while for appearing in the journal. And going on to another algorithm in 2012, you see, I'm not going to go over all this set of authors, and apologies for that because it's too long and I don't, I would probably make mistakes. But in any case, testing 1-2 freeness, so testing monotonicity can be done optimally in log n queries. Namely, log n queries are required and you can actually do that. So a matching lower bound is by Fisher in 2004. And it's really many different algorithms. Some of them are extremely beautiful. So that would really merit the talk by itself. I didn't do that. And for a larger pattern, so larger pattern was not considered. And the first time that it was considered in this scenario, property testing, is in slightly before 2019, where in a paper with Deepak and Yuri Rabinovich and Christian Zoller, we showed some results for larger patterns. So I will explain these results because here, the results that I'm going to describe today is a considerable improvement of these. Okay, so for monotone patterns, so we are talking now about larger patterns, so patterns of size 3 and beyond. And for monotone patterns, a monotone pattern is just a pattern 1, 2, 3 up to k. So there are only 2 monotone patterns, either the increasing one or the decreasing one. Actually, everything is known. So it can be done optimally in log n. That's a recent result by Ben Eliezer, Letzer, and Weigarten from 2019. It was already done in the 2019 original paper that I quoted before, but not with log n, but rather polylog, and it was improved in several papers. And for non-monotone general constant size pattern, this is our concern right now. So in the previous, in the original paper, we gave an algorithm that is n to the 1 minus 1 over k. So that's the amount of queries that it does. You see it's sublinear. It's still much better than n. So you don't need to query all the sequence, but it tends to n. And there was also a matching lower bound, but this matching lower bound was for the case where the algorithm queries all the queries at the beginning and then decides. Namely, it's a non-adaptive algorithm. It can't decide on the next query after it got the results of a previous queries. And that was not an optimal result. It was slightly improved, again by Ben Eliezer and another author, Canone, to n to the power of 1 minus 1 over k minus 1. And there's also a matching lower bound, again for the case of non-adaptive algorithms. But what happens for general algorithms? I mean, what's the real complexity here? And it was completely open, except for the case of 3. So for the case of 2, I told you that everything is known, but for the case of 2, every 2 pattern is monotone. So it falls into this monotone case. For the case of 3, that 3 is the first time that you get to see non-monotone patterns, like for example, the pattern 1, 3, 2. And already in the original paper, there was a polylog n query algorithm. It was adaptive, of course, because I told you, I mean, you could look 3 lines ahead above that you can't do better than n to the 1 minus 1 over k by non-adaptive algorithms. So for 3, there was a polylog n algorithm, but that was the only thing that was known for general non-monotone patterns. For 4, nothing better than the result tending to n was known. And the results in this work is that the following theorem, that for every epsilon and every k pattern pi, we can test the freeness in n to the little o of 1. So going much better than tending to n. It's not even n to the epsilon, or n to the delta, it's n to the little o of 1, and it's one-sided error. So let me explain this notion of one-sided error for a moment. So a one-sided error algorithm would be an algorithm.
Yes. That's little of 1 is in terms of k, or?
Yeah, there is a dependency in terms of k. There is actually a dependency in terms of k, but the little o of 1 there in the exponent is actually it's actually because of the dependence on epsilon. So the limiting behavior is the dependence of the epsilon rather than k. Okay. So because we fix k, and then for every small epsilon, we want the algorithm to work. So we actually get to the case where epsilon is much less than 1 over k, and the limiting behavior is determined by this epsilon. Okay. So maybe I'll say some words in the end if time will permit. Okay, so what's the one-sided error? So recall that we want to distinguish between 2 cases. The case where the function has the property, namely it's pi-free in our case, or it's far from being pi-free. And the one-sided error algorithm is an algorithm that never errs for functions that has a property. And why doesn't it err? Because it will always find the pattern if the function is not pi-free. Namely, if the function is far from pi-free, it will find a pi appearance, and then it will reject. But it can never find a pi appearance if the function is pi-free, so it will never reject a function that is pi-free, and hence it will only err on functions that are far. And that will be actually important. Okay, so for the purpose of this talk, so I'm not going to aim to do the whole thing here. I'm not going to show the n to the little o of 1 algorithm for every k. I am going to show only a square root of n algorithms algorithm, and not for any k, but just for k patterns. And that's already better from than the results before. And it exhibits the first main idea of the whole thing. And I will tell you what is needed besides what I will describe here. Okay, so from now on, we are going to concentrate on 4 patterns, any 4 pattern, and I will show you a square root of an algorithm, hopefully, with more or less all the details, or conceptually at least. Okay, so what is the idea? Excuse me. Okay, so the first idea, and that's an old idea, it used in all previous algorithms and in many, many other settings in property testing, is to consider the deletion distance instead of the Hamming distance. So what is the deletion distance? So getting back to the question that was raised before, the deletion distance is just the minimum size of a set of points such that f is pi free on every other point, on the complement of this set S. Namely, if you delete S, then the restricted F is pi free. That's the deletion distance. And obviously, by my definition, the deletion distance is at most the Hamming distance. So since I want to distinguish between functions that are far and functions that have the property, then if I will be able to decide whether the function is far in the deletion distance, then it's already okay, because the deletion distance is even smaller conceptually than the Hamming distance. And that's kind of obvious. But in fact, it turns out that it's actually equal, and it's very easy to see. I mean, it's very easy to see that for this specific property of being pi free, if you have a set and the function is pi free on the complement of the set, then you can always change the values of the function in the described set, in the specific set, to make the function pi free in the whole range, in the whole domain. Okay, so that's an easy observation, but it's quite important. And it's important because of the second fact, saying that if the deletion distance is d, namely, if you need to delete d points for the function to be pi free for a pattern of size k, it means that actually there are many pi appearances. There are at least d over k point disjoint pi appearances in F. And that's quite trivial. It's just the fact that, the heating set, or the, if you wish, the independent set in a hypergraph is at most the matching, right? I mean, the vertex cover is at most the matching times the size of the edge in the hypergraph. Okay, so that's kind of obvious. Okay, so our algorithms, as any previous algorithm, as I told you, accept unless it finds a pi appearance. So immediately it means that it is a one-sided error. And immediately it means that we only need to concern ourselves with inputs, with functions that are far from being pi free. And we already know that they have a linear number of pi appearances. And our goal is actually to find the pi appearance. That's the whole goal from now on. So we are given the fact that the function has a lot of pi appearances, a linear number of disjoint pi appearances, and our goal is actually to find them with high probability by sampling much less than n points, of course. So my goal, as I said, is going to be to sample square root of n points, or in fact, square root of n times some polylog. Okay, so here is the conceptual first step. And it's conceptual. It's not an algorithmic step, but bear with me for a moment. Suppose that I knew the whole sequence. Suppose that I would read the sequence. Then I would be able to form the graph of the sequence, which is just depicted here in this box. So this box is a box of size n, that's the x-axis, and the y is just the values of the points, and it's just a normal graph of the function. And of course, this box has n points in there because it's a function. Okay, good. So we don't know, of course, this box, but suppose that we knew this box. Okay. And I'm going to consider for this talk the fixed pattern 1, 3, 2, 4, which is non-monotone, you see, and there is nothing special about it. It's just to make clear what's going on. So the function that you see now on the right in this box has a 1, 3, 2, 4 appearance. And the way to see it, so in particular, these blue points show a 1, 3, 2, 4 appearance. And you see that this 1, 3, 2, 4 appearance, we can think about them as these 4 indices as I showed before, or we can think about them as 4 points in the grid having the relative order of the grid, right? Of the standard order in R2 in the plane. Namely, going northeast is going up. Okay, good. So here is the next conceptual step. It's still a conceptual step. Suppose that I had this grid, and now I want to partition the box into the one box that I had representing the function to square root of n times square root of n sub-boxes that more or less give me the picture, or at least a crude picture of the function. So what do I want from this partition? So I want that every column will be of size square root of n. That's easy because we know that the range, the domain is exactly n. So we partition it to square root of n disjoint columns. And we are going also to partition the range of the function, namely the y-axis, into square root of n layers, each containing square root of n points. So conceptually, of course, you could do that because there are n points altogether. So you could partition them into layers, each layer containing exactly square root of n points. I'm assuming here that the function is 1-to-1. It's an assumption that I didn't make before. It's not going to be really important. In the case that the function is not 1-to-1, I might have the whole points of the function just in one layer. So obviously then I can't partition it in this way, but that would be an easy case actually. So in the case that the function is not 1-to-1, it's going to be easy. So from now on, think about the function as being 1-to-1. So obviously I can partition it in this way. And if I partition it in this way, then I can tag each box. I have now n boxes and sub-boxes that I'm going to call maybe cells or maybe boxes. I'm going to tag them as empty, namely that there is no point of the function in this cell in the grid, or dense. Dense would mean that essentially all points in the column are in this sub-box. So there will be some threshold, but you can think about it as being very close to 1. And possibly, of course, it could be, a cell could be non-empty and non-dense. Okay, so I'm going to tag each box according to whether it's empty, dense, or none. And if I would be able to do that, I will get this picture. I will get that some boxes, now colored orange, are tagged as non-empty. So these are my non-empty boxes. Of course, that can't be the, yeah, well, it can't be the picture because you see that the third column here has no points, but of course it needs to have square root of n points, but it's just showing, say, yeah, I didn't color all the subboxes. Okay, is there a question at this point?
By the way, Ilan, so C2, for example, you said that yellow is dense, right? In this picture?
Well, no, I said that yellow is non-empty.
Ah, yellow is, okay. Okay.
Yeah, yeah. So that's why the third column can't be all white. But if I would immediately, it's going to become actually dense. So C2 could be that it would have two dense subboxes because actually the threshold is not going to be more than half. It's going to be, you know, depending on this epsilon. But it's really a constant.
Okay.
Okay, but yeah, okay. So at this point, conceptually, any set of, think about them as the non-empty boxes, and any set of boxes could be non-empty. In fact, it could be that all the n boxes are non-empty. Of course, I can't do that in square root of n queries, right? So that's why it's only a conceptual step, but suppose that I had it. Okay, and recall that I'm going to concentrate on this pi 3214. So if somebody showed me this picture, I could say, without knowing the points themselves, without having the actual points in the function, I could already reject and say, this function is certainly not 3213. Because if you look at these green boxes, since they are non-empty, then each of them contains a point, and it doesn't matter which point I take from any of these boxes, it will form a 3214 because the boxes, the green boxes themselves are 3214 in the order of the grid. So hopefully everyone sees that. So here I took a point in each of these green cells, and you see that this forms a 3214 in the function. Okay. So that would be conceptually, if I would do that, that would be a very easy case. I would look at these boxes, and if I see a set of 4 boxes forming 3214, as I showed here, then immediately I could reject. I could say the function is not pi free. And we say in this case that there is not only a pi appearance, but there is a pi box appearance, because the boxes themselves already have 3214 appearances. So every time that I have a pi box appearance, I have also a pi appearance. But the other way around is not correct. I mean, it's not an equivalence. So let me just maybe, where did I say it? Well, I didn't say it. So I'm just telling you at this point that in the other way around is not true, because I could have a pi appearance with 2 boxes sharing the same layer or the same column. And then I don't know. I mean, then it depends on the actual relative order among the points in the boxes and not just the location of the boxes themselves. So we will come to that later. Hopefully. How am I doing with time? Good. Okay. So I told you that this all is conceptual, but now I'm going to tell you that we actually can get this picture. So this gridding can be done in essentially log n queries, although there are n boxes. And to say it more exactly, I can either do it in square root of n queries, or if I'm not successful in tagging the boxes in the way that I wanted, then it means that are at least square root of n times log n non-empty boxes. And actually, this is very easy. I mean, this claim is very easy. It's just by sampling. So if I'm going back, what do I do? What do I need to do in order to do this gridding? The columns are set. I mean, the columns are easy, I told you. I mean, we just partition the set n into n disjoint sets of square root of n. How do we form the layers? So just by sampling square root of n points, or relatively, I mean, essentially square root of n points, like say 100 square root of n points, you expect that 100 points will be in every layer. So you would define the layer by taking the first 100 points and then the next 100 points and so forth. We are going to use log n times square root of n points, so to minimize the overall error in this tagging. But this is essentially just sampling. So the pictures that you see here is kind of misleading. The layers are, of course, not of equal size, because the range is infinite, right? I mean, it's just R. But in terms of the number of points, they are of constant size. They are of the same size, identical size. Okay, so that's easy to be done. I mean, if you didn't really get it, it doesn't really matter. I mean, that's easy. So we either find out that there are at most essentially square root of n non-empty boxes, or there are much more than square root of n log n boxes, and then something wrong is happening for us. But let's see what we are going to do in this case. So that's an important lemma that we are going to use in the case that a lot of boxes, that we have more than square root of n non-empty boxes. And the lemma is a lemma of Marcus and Tardosh solving the Stanley conjecture for exactly pi freeness. And the lemma is not very complicated. It says the following, that for every k, there is a constant, another constant, tau, depending on k, such that if there are more than tau of k times square root of n non-empty boxes, then there are k boxes forming a pi box appearance for every pattern pi of size k. Namely, if we are at the case where we have more than square root of n times log n non-empty boxes, if we already found square root of n times log n non-empty boxes, by this lemma of Marcus and Tardosh, we already know that there is a pi appearance, because there is already a pi box appearance. So we can rule out this situation. Okay, so here is what I said. That's summing up. We conclude that either we find a pi box appearance within the non-empty boxes, or there are at most a linear in square root of n dense boxes that cover almost all points.
Ilan?
Yes.
In the Marcus Tardosh paper, is it algorithmic? I mean, does it specify the square root n? Does it specify the k pattern?
No, it's not algorithmic.
No, because you wanted to exhibit, right?
Right. But I already have these boxes, right? So if I have these square root of n boxes, I mean square root of n log n boxes, I'm just going over these square root of n boxes and just check it, right? The time the time doesn't matter for me. I mean, and it's of course linear, right? I mean, it's linear in the but well, I mean, but actually, it's a good question. I didn't talk about suppose that I have that I know the whole sequence. How do I find a pi appearance? How do I decide whether there is a pi appearance or not? But I'm not going to consider this question, right? I mean,
you're only interested about the queries, right? Okay.
Yeah. I'm only interested about the queries, right? Yeah. Okay. So, but in fact, it can be done in linear time. I mean, actually, that's not so easy, but it can be done in linear time. For any pattern pi in linear time in the sequence, you can find whether it's pi free or not. And now the sequence is going to be of size square root of n, or square root of n times log n, because it's just the number of boxes. It's just the boxes. Okay. So actually, it can be done in linear time. in square root of n. Okay, so we are in this conclusion in the or part below that there are at most linear in square root of n dense boxes that cover almost all points. And the reason that they cover almost all points is that it's because we did sampling. And so it could be that some, you should think about it as a negligible number of boxes contain points that we didn't find at all. But they won't matter. Okay, so here is this here is the steps that we are going to do in order to clean this fact. So we choose some appropriate constant C and delete every row that contains more than C dense boxes, because on the average we have linear in square root of n. So I'm sorry. So we already assumed that we have at most square root of n, order of square root of n dense boxes. So on average, we have constant number per column and per row. So we don't expect that many rows will have more than some constant and many columns will have more than some constant. So we delete every row that is atypical and every column that is atypical, every column that contains more than C dense boxes. So as a result, every column and every box will contain at most constant number of dense boxes, and we don't lose a lot of points. And our goal is still to find the pi appearance. And we are hopeful because we had a lot of pi appearances to begin with. And now we have deleted not too many points, so we can't delete a lot of these pi appearances. And so we still have chance. Okay, good. So this is what I said, and I'm not going to dwell over that. And now I need to define this notion of connected components of boxes. So for two boxes, B and B prime, we say that B and B prime are in the same connected component, if you wish, if they share a row or a column. So going right, I mean, going in the same row or going in the same column, that's, if you wish, this define a graph. And the connected component is just the class of this, the transitive closure of this relation. So here is a picture. So here is a set of boxes. And you see there are three connected components. This set of boxes is partitioned into three connected components. The blue one, because you can move from any blue to any other blue by going along column or along rows. And the green ones are a different connected component, and the red one is also a different connected component. So I hope that this is clear. And if we go back now, remember that we sometimes, the easy case was that we found a pi in 4 boxes, none of which share a column or a row. And we call that a pi box appearance. It was exactly a pi box appearance because none of the boxes shared a column or a row. So we didn't care about the actual placement of the points in the box. And in that case, this is a configuration of 4 components. So it's a pi appearance in 4 components. And we also note that if we count the number of components, since every column contains a constant number of boxes and every row contains a constant number of boxes, there are linear number of components of size at most 4. Just think about it as a graph of constant degree. So you have a constant number of connected subgraphs of size 4. Okay, so if you have a pi appearance in 4 boxes, then you are already done. That was our easy case. But it does not mean that every pi appearance is such, and it could be that none of the pi appearances are such. So here is a picture of, again, this pattern 3 to 1, 4. And you see that this pattern 3 to 1, 4 it appears in actually two components. The top layer has the 3 and the 4 in one component because these two boxes share a layer, and the 2 and the 1 are in another component and they share a layer. And just looking at these boxes, I couldn't guess that there is a 3, 2, 1, 4 there. So an appearance could be in any number of components between 1 and 4, because we are talking about a pattern of size 4. So here is a picture of some different configurations. So on the top left, you see the pictures that I showed you before. It's a 3, 2, 1, 4 appearance in two components. Next to the right is a 3, 2, 1, 4 appearance in one component, two boxes, but one component. Then next to the right, it's a 3, 2, 1, 4 appearance, again in a one component, but in just one box. And below, there is a 3, 2, 1, 4 appearance, again in two components, but in a different way. You see the 3, 2, 1 legs of the appearance appear in one box, and the 4 in one component, and the 4 appears in a different box in a different component. Okay, so since we have omega of epsilon n disjoint appearances, this is what we assumed at the beginning. I told you that that's a fact. That was this fact number 2. There are a lot of appearances either that form a one component, or in two components, or in 3 components, or in 4 components, of course, but this we already ruled out because that we already discovered by our gridding procedure. So our gridding procedure gave us this map. Remember this colored map of boxes. Okay, so what do we do now? So we are going to analyze each of these situations. So if we happen to have many appearances in one component, this is what we do. Of course, we don't know which of the situation we are at, but one of them must happen, and we are going to do all of those one after the other, right? So assume first that there are a lot of appearances just in one component. Then by averaging, there are square root of n many one component configurations, each containing at most 4 boxes, because a component contains at more 4 boxes to be relevant for us, and each containing omega of square root of n pi appearances, because altogether we assume that there are linear in n appearances, and if most of them appear in one component, and I have only square root of n components, it means that the typical component will contain a lot of configuration, right? Corresponding to its size. So square root of n many components. So sampling a component is likely to result in such a component that contains a lot of appearances. It doesn't matter at this point that it contains a lot. What it matters is that it contains any, because at this point, after we sample the component has only square root of n domain points, right? Because it contains at most 4 boxes, and each box is of size square root of n in the domain. And so we just query all points there. And we queried square root of n points, order of square root of n points, and we must find a pi appearance. So that takes care of the case that many appearances are in just one component. Okay, what happens if many appearances are in 3 components, like the case that is depicted here? So if many appearances are in 3 components, every 3 components for a 4 pattern must behave like that. There is one component that contains 2 points of the pi, and the other 2 components contain the single point, namely they are just a single box. So again, by averaging, there are linear in square root of n many such components, so order of square root of n, that contains the 2 1 points, like is depicted here. So what we will do is, again, we will sample such component, the yellow ones that contains the 2 1, and we will run the monotonicity testing, because this is just discovering the 2 1 legs. And any box, any 2 boxes, non-empty boxes that can augment this appearance into a pi appearance is okay for us. And we know that there are many, so we will find it. So that's this closes the case for many appearances in 3 components. So that might be a good point to stop for a moment and take a question if there is any.
Ilan, I would just want to make sure the difference between whether the pattern is 1, 2, 3, 4 or 1, 3, 4, 2 or so on is really not significant here, right?
Well, no.
Except for
in this analysis, it's completely not significant. The reason that for monotone pattern it's so easy is that the monotone pattern can be cut anywhere, and it results in 2 sub-monotone patterns that can be glued together. And in a general pattern, we don't have this phenomena. So this what makes non-monotone patterns much harder to test. But in my analysis here, it tests any pattern.
That's what I thought.
So you are right. I mean, from this point of view of descriptions, there is no difference between any pattern, any 4 pattern.
But you might have a case if you were, say, looking at the case of patterns of length 12. That you
but I'm not describing it. So at that point,
then you might have things that are monotone going up and down, which
exactly,
would be different than zigzags.
Right.
But we don't want to get into that.
Yeah, not at this point. So I will say some words. I mean, so our result includes that case, but right now I'm not going to tell you anything about it. Okay. So what about 2 patterns? So I discussed already appearances in 4 components. That was the easy case, the very easy case, where you had a pi box appearance. I discussed the case of 1 component. I discussed the case of 3 components, and what happens when I have 2 components. So in 2 components, that's the hardest case, as it turns out. So I'm showing here 2 cases. When I have, so look at the picture on the left. So here I have an appearance 3, 2, 1, 4 that appears in 2 components, the 3 and the 4 in 1 component, and the 2 and the 1 in 1 component. And if somebody told me that there is a 3 and the 4 in the top component and the 2 and the 1 in the bottom component, I might conclude that actually there is a pi appearance in the whole box, a 3, 2, 1, 4 appearance. But that's not true. So if you look at the case in the right, again, there are 2 components. There is a 2 and the 1 in the bottom component. There is a 3 and the 4 in the top component, but altogether they don't form a 3, 2, 1, 4 appearance. Okay, so it's a harder case. It's not enough to know the partial appearance in every component in this case in order to conclude that there is a full appearance, a full pi appearance, but I actually need to know where the legs of the specific partial appearance appear in the component. Is it true that it can be glued together so to form a whole pi appearance? So hopefully this thing was clear. So the comment here is, by averaging, just as before, there are many components that contain a 3 and a 4. And there are many components that contain a 2 and a 1. And possibly they could be glued together, but possibly not. So it's not enough to find a 3 and a 4 or a 2 and a 1 in every component or both. We also need to know the partial assignment of the legs of the appearance in the box or in the boxes, in the particular boxes of the component. So that's the but here. The but says that they these appearances not necessarily form a 3 to 1, 4 appearance. Okay, however, we know that there is some matching between two components. If most of the appearances are in two components, there is some matching of one component containing the 3 and the 4 and another component containing the 2 and the 1, so that they will form altogether a 3 to 1, 4. Because we assume that there are a lot of 3 to 1, 4 appearances in two components. So there is such a pair. So what we find ourselves in the need to do here is that instead of just sampling one component or a constant number of components as before, we are actually going to check here for every one of the square root of n components for a 3, 4 and a 2, 1 appearances for all of them, okay, in parallel. And it turns out that we can afford that because I told you that monotonicity testing can be done in log n. So it can be done in log n per component, and we have square root of n components. So overall, this is tilde square root of n. So essentially, the order of square root of n. So I can do that for all components in parallel to test for the sub-pattern appearances of size 2. And then after I tested all of them, then of course I will find the 2 that match. And I'm guaranteed that there are 2 that match, that form together the 4 pattern. Okay, so here I found an appearance. Okay, good. So that's it, essentially. That's it for the square root of an algorithm. So at this point, the square root of algorithm should be more or less clear. So if I'll sum it up, we are going to do the gridding that I told you that we can actually do in order of square root of n times log n. And we either find a lot of non-empty boxes, and we are done because of the Marcus-Tardos lemma, or we find only square root of n dense boxes, meaning that the average per column and per row is a constant, and then we delete atypical columns, delete atypical rows, we still remain with a lot of points, and then we look at the 3 cases. Either the appearances are in one component, so we sample just one component and look at all the domain points in it, or we sample one component and look for a partial 2-size pattern and try to augment it with 2 other components because the appearance is in 3 components. And in the 2-component case, we just test every one of the square root of n components, order of square root of n components for 2-size patterns, for the 2 possible 2-size patterns, and try to match 2 of them to form together a 4 pattern. Okay, so that's a square root of n algorithm for 4 points. So that's another good point to ask questions. And
so, Ilan, is it that we will be checking one after all these cases, one after the other?
Yeah, we just check all these cases one after the other. In fact, just in parallel, right? I mean, we sample. So for the first 2 cases, we just sample a component and look at all the points in it. It's just square root of n queries. And for the other case, we sample log n points from any component, from every component, and test for the 2 patterns. And then do calculations. But the queries, I mean, I told you that I'm measuring the number of queries, so I'm set with, I just did the queries. Okay. Okay, good. So what's next? By the way, you can ask yourself, why is it adaptive? So the adaptivity is because of the fact that I first do the grading, and only then I know what are the components. So only then I know how to sample a component and do these three cases that I told you. Okay, so how do I improve it? So I'm going to be very brief here, just tell you the difficulties and the ideas, or some of the ideas. So one thing is how to deal with only just 4 points, 4 size pattern. And the reason to restrict for 4 size pattern, which is not general, is that we saw that the hardest case for 4 size patterns is that it splits into 2 components of size 2. And size 2 patterns are very easy. We already knew that we could do in logarithmic number of queries because of monotonicity testing. But for larger patterns, when I break it into 2 components, like if I will look at, say, pattern of size 12, if I break it in 2 components, this will be of size, it could be of size, say, 6 and 6, or 4 and 8, or whatever. And for these, I don't know how to run an efficient test. So it seems that I can't afford to do all the tests for all the components. So let me just restrict myself to this simple 4 case for a moment. And how do I go beyond the square root of n bound, which seemed maybe possibly essential here, but it's not. And the reason it's not is that instead of grid the initial box into square root of n times square root of n boxes, I will grid it into n to the delta times n to the delta boxes. So namely much larger boxes, but few of them. And this can still be done by the same reasoning in time or in number of queries that is proportional to the n to the delta now, instead of n to the half. Okay, so the gridding can be done much more efficient. Of course, I will remain with much larger boxes, and I will not be able to afford to query all the domain point in a box. Okay, but this doesn't matter because sampling a box, like I did in the cases before, I will not be able to sample all points, but I could do now recursion on the component that I will sample. So the way to go down to n to the delta is to do much coarser gridding on the first recursion level, and then recurse on just one component. Okay, and that was for the cases of 3 and 4 components, just as before. For the case of 2 components, I will still have to look for all the components and do the size 2 patterns, but this took log n queries and not n to the delta and not square root of n. So this I could still afford to do. And so the whole thing will become, if you solve the recursion, will become, if I do the gridding to n to the delta times n to the delta, it will become n to the 2 delta. So I could set my delta to be as small as I want and get a much lower complexity algorithm. Okay. Okay, so this is what I said, just very briefly. What do I need to do in order to go for larger patterns? So for larger patterns, there are 2 problems. So one of them is this recursion. And in this recursion, I'm losing the number of appearances in every step that I took. So the recursion depth is somehow limited. But a more serious problem is that I showed you that sometimes the leg appearance in the component matter. And so it turns out that we need to solve a seemingly harder problem. In fact, it is a harder problem because we don't know how to solve it. So let me try to explain to you what is this problem. So now think about even a much simpler case, just a three pattern, not even a 4 pattern, just a 3 pattern. So in a 3 pattern, I'm just looking for, say, this pattern 3, 1, 2. I'm looking for 3 points, a maximum, a minimum, and then to the right, a value in between. So it's a 3, 1, 2, right? Now, a pi-free or a function that is not pi-free should have such appearance somewhere. And if it's far, it has a lot of such appearances. Okay, but what if I would want actually the following problem? I would want to find a 3, 1, 2 appearance, but not anywhere. I would want to find a 3, 1, 2 appearance so that the 3 and the 1 legs are in the first half of the domain points, that is in the 1 to n over 2 places, and the corresponding 2 of this appearance appears in the n over 2 plus 1 up to n places. Namely, I'm specifying more, I'm restricting more the places where the appearance might be. So of course, it could be that the function will have a lot of 3, 1, 2 appearances and none of the special case that I want. And I actually find myself in need to solve this more restricted case. And now there's a problem because the Marcus Tardosh doesn't hold anymore. And it seems that everything breaks. So here is what I said. It could be that there are many 3, 1, 2 appearances altogether, but none in this restricted form. And Marcus Tardosh doesn't hold anymore. Okay. And in fact, it is harder. And we, as I said, we don't know how to solve it. But it turns out that we can come out with an intermediate problem between the pi appearances and the more specific pi appearances where I fix the appearances of the legs. And somehow all our methods work for this intermediate problem, so we can still solve the pi appearance problem in sublinear time, in strong sublinear time, in n to the little 1 over n, n to the little o of 1. And that's it. So thank you very much.
Thank you, Ilan. Big round of applause. You can unmute yourself and put it on your cameras and open up for additional questions if anyone has additional questions.
Okay, so thank you again for listening.
I guess we had the questions during the talk. So thanks again very much, Ilan.
Thank you.
Okay. And everyone take care.
Yeah, bye then.
Very great talk, Ilan.
Thank you.